start with a story about discovery. Papy found himself in a mathematical conundrum, grappling with the elusive concept of finding a derivative when a function is inside another. The weird-looking function on his paper seemed to twist and turn in ways he couldn't fathom, leaving him scratching his head in bewilderment, frustration and self-doubt. Determined to unravel the mystery, Papy decided to take a hike through the woods on his favorite trail, hoping the tranquility of nature would somehow spark a eureka moment. As he wandered beneath the towering evergreen trees, he pondered the complexities of the weird function that had eluded him for hours. Soon, hours turned into many more hours, and Papy's frustration grew with every step. The mathematical riddle seemed unsolvable, and he began to question his math ability and wondered if he would ever find the derivative or if calculus was this enigma that only the brightest could see. Just when he was on the brink of mathematical despair, Papy stumbled upon a large rock, and atop it sat a pregnant woman gazing at the majestic Olympic mountains. Intrigued by her serene presence, Papy couldn't help but approach her and share the weight of his mathematical woes. With a sympathetic smile, the pregnant woman listened as Papy poured out his mathematical struggles. She asked if she could look at the problem, and as her eyes scanned the perplexing function, she let out an amused chuckle. "Oh, Papy," she exclaimed, "when you saw me, what did you notice?" Baffled, Papy replied, "You're pregnant?" The woman's eyes lit up with excitement, and she declared, "Exactly. And that's why you can solve this problem, because this problem is pregnant like me." Papy blinked in confusion. "Wait, what do you mean?" With a mischievous grin, the woman began to explain, "You see, just like a pregnant woman carries the potential for new life, this problem carries the potential for derivatives within it. It's pregnant with possibilities." Papy's eyes widened as he tried to wrap his head around this unexpected analogy. The pregnant woman continued her metaphorical explanation, drawing parallels between the growth of a baby and the development of derivatives within the intricate function. She shared how she learned derivatives from her math teacher, Mr. Lovelace, and how he taught her to look for functions that required a special rule, the chain rule formula.
Hello everyone. We're being asked to differentiate this function with respect to x, and this function is y equals the quantity 2 minus x to the fifth to the ninth power. Now when I see this function, I actually see two functions, 2 minus x to the fifth, and something is being raised to the ninth power. I see something that's inside, and I also see something that's outside. Those are composite functions. When I am taking the derivative of composite functions, often I like to look at this as, hey, there's something inside. Well, you know what? That's like having a little baby, right? So this right here is what we're going to call our baby. And the outside, that's going to be mom. Okay? So what we're going to do when we take the derivative of this function, we need to first determine, hey, what's mom? Mom is going to be something to the ninth power. And our baby, the inside, is going to be 2 minus x to the fifth. That's going to be our inside and outside when we're going to take our derivative. Now let me get rid of this stuff here, and let's go ahead and take the derivative. I'm going to take the derivative of the left side, which is y, and I'm also going to take the derivative of the right side, which is 2 minus x to the fifth to the ninth. When I take the derivative of the left side, I'm going to get dy dx. Okay, that sounds good. Now I'm going to take the derivative of the right side. Now this is going to be a little different because I just can't use the power rule. I'm going to use something called the chain rule because I have an inside and an outside. And basically what we're going to do is take the derivative of the outside times the derivative of the inside. Well, basically, we're going to take the derivative of mom times the derivative of the baby. So when I look at this, I want to take the derivative of mom, which is 9 times that quantity to the 8th. Okay? But remember, mom is pregnant, right? Mom, so she has a baby. So we're going to keep the baby. She keeps the baby. Times the derivative of the baby, which is going to be negative 5x to the 4th power. And so what I've done is I've taken we'll put this in a different color here. I'm taking the derivative of mom, and I'm going to multiply by the derivative of the baby. I'm going to take the derivative of the outside times the derivative of the inside. Now let me get rid of this information here. And let's clean this up a little bit. And we have that, we know that dy dx is going to equal negative 45, 9 times our negative 5, times x to the 4th times the quantity 2 minus x to the 5th to the 8th power. And that's our derivative. So let me put a box around that to make everyone know that that is what I'm saying is my conclusion. All right, let's do another problem here. We're being asked again to differentiate this function. This function is y equals the cube root of 1 minus 8z. And you can see that it's a little bit obvious on this one what's the inside and what's the outside. But because I have the inside and the outside, I'm going to have to apply the chain rule. So why don't we first decide, hey, what's the end outside? That's mom. So we determine that mom is going to be the cube root of something. And let's just go ahead and use the different notation. This is radical form. Let's put this in exponential form, which will be something to the 1/3. Because that'll be a little easier for us to take the derivative if we have it in exponential form. And then the baby is going to be the part that's inside, and that's 1 minus 8z. Okay, so I have mom, I have the baby. Let's go ahead and take the derivative. And I have the derivative, I'm going to take the derivative of the left side times the derivative of the right side, but we're going to put that in exponential form, okay, because there's mom and there's the baby, okay. Now, when I take the derivative of the left side, that is my dy dx, and when I take the derivative of the right side, I'm going to bring down that power and subtract 1, which will give me negative 2/3. That looks weird. This is mom, so she keeps the baby. Remember, she's pregnant, so we got 1 minus 8z times the derivative of the baby, which will just be negative 8. So now we have taken the derivative, and technically this is our derivative. It's just maybe not in a very usable form, but you know what? It is our derivative. So let's just clean this up a little bit, and we have dy dx, which equals negative 8/3 times 1 over 1 minus 8z, and that is going to be the cube root of that. That's not times, but it's going to be to the 2nd power. Okay? And let's clean it up one more time, one more row of, making it look a little bit better. So I see that my numerator is going to be negative 8 all over 3 times the cube root of 1 minus 8z, and that is being raised to the 2nd power. Now, one of the reasons why we like to write this in this form is because you can see that in this fraction, your numerator is going to always be negative. And if you look at your denominator, you see that 3, which is positive, and something squared. So that's positive. So just by analyzing and take a look when it's in a certain form, you can look at this and say, wow, wait a minute. If my numerator is always negative and my denominator is always positive, a negative divided by a positive is going to be negative. So that tells me something about this derivative. It tells me something about the slopes of these tangent lines. And it's really important to start recognizing, okay, we're taking the derivative, but also being able to take a look and see what's going on. Okay? Let's do another. All right, let's do one more problem. We're being asked to differentiate this function f of y, which equals the natural log of the quantity 1 minus 5y squared plus y cubed. Now, this is a little different. It's not trig. It's not a polynomial function. This is a natural log. And it's a little different, but it's at the same time, we can see that we do have the natural log function, and we also have a function that's on the inside. So it's pretty obvious what's the inside and what's the outside. We have composite functions, which is going to require us to use the chain rule. Now, one of the things that I like about the natural log is when you take the derivative of it, the derivative is simply going to be, if I take the derivative, it's simply going to be 1 over the baby times the derivative of the baby. So we need to determine what's the baby. And be able to take this derivative. So let me clean this up a little bit, and let's go ahead and find this derivative. So we have the derivative of the left side, which is going to be f prime of y. And we're going to take the derivative of a natural log, which is 1 over the baby, 1 over the inside, times the derivative of the baby. Now, this time I'm going to just go ahead and just write the derivative of the baby. Okay? And one of the things that I like about writing it like this, that's a squared plus y cubed, is that when I look at this to try to catch any mistakes that I'm making, I can look at this quantity right here and see that that quantity is the same as this guy right there. And that may help me catch any of my mistakes later on. Okay, so let's continue. Let's change that back to our white. So we have f prime of y is equal to 1 over the baby. He's done. This part of the expression is done. But now let's take the derivative of the baby, which is going to be negative 10y plus 3y squared. And again, this is our function, our derivative of our function. We're just going to clean it up a little bit, and we see that f prime of y is equal to negative 10y plus 3y squared all over 1 minus 5y squared plus y cubed. And you know what? There's my derivative. But you know what? I'm going to put this and make sure these expressions are in standard form. So we want to make sure they're in descending degree. So let's look at 3y squared minus 10y over y cubed minus 5y squared plus 1. And that helps me a little bit because I can now analyze this function a little bit better and see that when I look at this guy right here is nothing but 3 over y. So that tells me that, hey, this derivative here is decreasing. it's approaching zero. And that tells me something about the behavior of the derivative, which consequently tells me something about the behavior of the original function. So it's always important to just kind of, not only we're trying to come up with all these different techniques like the chain rule, and the power rule, the product rule, and all of these different rules that we have, but we want to also be able to analyze the behavior of our function by looking at our derivative. Well, I hope that helps you, okay? But that's the chain rule. Remember, the chain rule deals with looking at composite functions. And what we do is simply take the derivative of mom times the derivative of the baby.
As the pregnant woman spoke, Happy's confusion began to dissipate. Suddenly, the chain rule seemed less like an elusive beast and more like a journey through the intricacies of mathematical creation. Leaving the woods with newfound insight and a quirky metaphor, Happy couldn't help but chuckle at the unexpected encounter that had turned his mathematical despair into a whimsical adventure. And so, armed with the knowledge to see that his problem was pregnant, Happy eagerly returned to his mathematical endeavors, ready to tackle derivatives with a newfound perspective and a smile on his face.
Thank you for watching. Please like and subscribe to my channel. It really helps me to continue making videos that celebrate learning and embrace the beauty of mathematics. See you in the next video.